What's up, guys? This is Jahangir from Emporium, and today we're going to be talking about our valence bond theory. So there's two theories or models we're going to be talking about of how these molecules create bonds, and the first one is valence bond theory. In our later video, we'll talk about molecular orbital model or molecular orbital theory. So valence bond theory is this idea in which we're going to have these atomic orbitals, and let's say this is hydrogen and this is hydrogen. So when these two hydrogen combine, we're going to have H2, or we can think of it as hydrogen gas. Now the way that they combine is, let's say both of them have their own valence electron, and both of these are going to be the 1s orbitals. So when we're looking at valence bond theory, we're looking at these atomic orbitals, and when these two atomic orbitals combine, which is what creates that covalent bond, we're going to see a structure sort of like this. And it is this overlap of those two atomic orbitals that creates this covalent bond in our valence bond theory. Now, in our valence bond theory, and I'm just going to write this over here, our electrons are localized. So if we remember from our past videos talking about localized and delocalized electrons, these localized electrons are going to stay in a certain position, and they're going to be in a region formed between two of these atoms, so maybe somewhere over here, whereas delocalized is going to be shared, and these electrons can actually be in an area in that molecule. So the bonds that we're going to be talking about separate from sigma and pi bonds. So sigma bonds, and this is the sign for sigma. Sigma bonds are going to be formed, and I'll put sigma bond. These are going to be formed every time we form a bond. So if we have H over here, we write the Lewis structure of hydrogen gas, something like this, there would be one sigma bond. Now pi bonds come into play. So pi bonds come into play when we have double or triple bonds. So when we have more than one bond. So it might be something like CO2, where we have these double bonds, and I'm not gonna write the whole Lewis structure of CO2. We'll actually talk about that in terms of hybridization. But just looking at these sigma bonds and pi bonds, if we have a double bond, that means we have one pi bond. If we have a triple bond, that means we have two pi bonds. So for every bond we have, whether it's double, triple, or single, we're always going to have one sigma bond. And if we have more than one, and we have two bonds, for example, a double bond, we're going to have one pi bond. And then if we have triple bonds, we have two pi bonds. So expanding on our idea of how these atomic orbitals overlap to form our covalent bond, we also need to talk about the idea of hybridization. So hybridization is this idea in which we can actually combine these atomic orbitals to create a hybridized orbital. So to really illustrate this, let's look at methane, for example. So methane is CH4. And to really illustrate hybridization, let's write the electron configuration of carbon. So the electron I'm just going to put con as electron configuration just to shorten that out. Electron configuration of carbon. So we first start out with 1s, and we fill in both of those orbitals. So remember, in our Pauli exclusion principle, in our Hund's rule, with a Pauli exclusion principle, we want to make sure that both of these electrons are in different spins, they're in opposite spins. And we look at 2s, which we're going to have same story over here. And then when we get to 2p, we have to fill three of these over here. So according to Hund's rule, we have to fill in each one until they have an electron, and that is our electron configuration of carbon. Because if we look at our periodic table and we see how many electrons carbon has 6 electrons. So this is the electron configuration of carbon. Now with hybridization, what we're doing is we're pretty much forming a new orbital in which we can fill these 2p orbitals. So what happens is, with this hybridization, one of these electrons over here will move to, let's say that's 2pz, for example. So what's going to happen is we're going to have our 2s, which already has that one electron over here, but now we have 2p, and we could say this is x, 2py, 2pz. And remember that each of these spaces fills in those p orbitals, because in our p orbital we have three different types of orbitals. We have x, y, and z. So each of these are going to have one atom, and or one electron, sorry. And as you can see, this is a perfect example of our sp3 hybridization, because we have an s orbital over here and we have 3 p orbitals. So we know this is sp3, and we have 1, 2, 3, 4. So we have 4 sp3 hybridized orbitals, or we can just say that this methane over here is sp3 hybridized. So what this is going to look like is, if we have their carbon over here, and let's say that's our carbon, then we're going to have this P and S right here. So this is sp3, and over here we're going to have the same story, sp3, and since this is our tetrahedral Vesper model, we're going to have that sort of structure, and we'll have this. So this is our P, this is our S. This in total makes our sp3 orbital. And just looking at, and let me actually put hydrogen, hydrogen, and hydrogen just to help you guys understand that. But over here, you don't really have to go through all of this math or look at the electron configuration and try to move the electron over here, because looking at this methane over here, or looking at just the Lewis structure of a molecule, any molecule you're looking at, here's a trick you can use to understand the hybridization of, let's just say, carbon. So you're going to want to attach each letter to each bond. So with all of our hybridizations, we're only going to have one S. So we're only going to have one S that we could put, but we can put as many P's as we want. So what this means is, what you could do is, looking at each of these bonds, you could attach this as S, then P, 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 and then you know that it's sp3 hybridized. And if we want to calculate the amount of sigma bonds there are, well, we have 1, 2, 3, 4. So we have 4 bonds in total, and we don't have any double bonds or triple bonds, so we know we don't have any pi bonds. So overall, we're going to have 4 sigma bonds. All right, so now let's go through some practice. And I'm going to use carbon dioxide as our example for this one. So this is COO. And the Lewis structure looks sort of like this. So I want you guys to pause the video and see if you can identify the hybridization of carbon, as well as the amount of sigma bonds and pi bonds there are. Alright, so if we use our little trick of trying to identify the hybridization, we can just attach S and P over here, knowing that carbon is sp hybridized. Now, if you look at oxygen over here, for example, and I'm just going to erase these over here. So for oxygen, we're going to have S, and each of these lone pairs we can represent as a region where we can put our P. So this would be P, P. So oxygen is sp2 hybridized. So just a simplified way of understanding this method is that you have to look at the element that you're trying to find hybridization over. And first you want to calculate how many atoms it's actually bonded to, how many other elements it's bonded to, as well as the lone pairs. And that's when you can find the hybridization. So I'll write this over here. So the hybridized orbital, to find that, it is going to be the number of bonded atoms. So number of bonded atoms. This is going to be plus the amount of lone pairs, if there are any. So lone pairs. And this makes sense, because if we have 4 bonded atoms, then we're going to have sp3 hybridization. Or if we have 2 bonded atoms and 2 lone pairs, then that would be the sp3. If we had 3, this would be sp2, and if we only have 2, this would be sp. So hopefully that helps you guys understand that portion of the hybridized orbitals. And now let's actually identify how many sigma bonds and pi bonds we have. So we automatically know we have 2 bonds, so we know we have 2 sigma bonds, because for every bond there's always going to be 1 sigma bond. So we automatically know we have 2 sigma bonds. And since we have 2 double bonds, that means we have 2 pi bonds. Because if you want to visualize it like this, and if we want to do the same sort of method we've been doing with these hybridized orbitals, you can think of one of these as our sigma bond over here, and one of these as our pi bond. And we do the same thing over here, sigma, pi, so we get 2 sigma bonds, 2 pi bonds. Alright, so now we got some practice. So I want you guys to pause this video and see if you can find the hybridization and number of sigma bonds and pi bonds for each of these molecules. And as a hint, you really want to draw out your Lewis structure. So let's start with NO2 over here. So we're going to have a nitrogen, and there's obviously going to be a bond between these oxygens. And to fill this octet rule, we're going to try another bond over here on that oxygen, and that fills the nitrogen's octet rule as well as the valence electrons. So we're going to have this oxygen filling its octet rule and valence electrons, but this oxygen over here is going to have a negative formal charge, which is how we get our overall negative charge on our NO2. So this is our Lewis structure for NO2 minus. Now, if we want to find our hybridization of nitrogen, if we look back at our equation, which is number of bonded atoms plus lone pairs, how many atoms are bonded to oxygen? We know that that's 2, and there's also a lone pair. So that means we have nitrogen is sp2 hybridized, and you can think of it as spp. So nitrogen is sp2 hybridized. This oxygen over here, and this oxygen specifically, is sp2 hybridized as well. But this oxygen over here is spp. So this oxygen over here is sp3 hybridized. Now let's look at the amount of sigma bonds and pi bonds there are. Since we have this double bond over here, we know we have one pi bond. So we have one pi bond, and then there's 2 bonds in total. So we're going to have 2 sigma bonds. Now let's look at 2 over here, and to draw out that Lewis structure, we're going to have a carbon in the middle, and we could say that that's a double bond over here. And one of the things you'll notice is that as you go through as much practice as you can with these Lewis structures, you can pretty write them out subconsciously. So over here with this carbon, that hybridization is spp. So the hybridization of our CH2O is going to be sp2. The carbon is sp2 hybridized. And let's see the amount of sigma bonds we have. We have 1, 2, 3. We have 3 bonds in total, so we have 3 sigma bonds, and we have 1 pi bond. Now let's look at this molecule over here, C2H3N. So when we're looking at these, let's just draw out the atoms just out of the blue. And first, this carbon has already filled in its valence electrons as well as octet rule. We don't have to worry about that. But this carbon over here connected to this nitrogen hasn't filled its valence electron or octet rule. So what we could try to do is form a double bond and see how that goes. But with this double bond, both the carbon and nitrogen haven't filled their octet rule or the amount of valence electrons they have. So if we try a triple bond over here, then that actually fills in the requirements we need, and this nitrogen over here would just have a lone pair. So this carbon fills its valence electrons and the octet rule. So all we have to do is ask ourselves, what is the hybridization of the carbon? So this carbon specifically is going to be sp3 hybridized, while this carbon over here is sp2 hybridized. Now, to see how many sigma bonds and pi bonds we have 1, 2, 3, 4, 5. So we have 5 sigma bonds, because that's how many bonded atoms, you could say, the amount of bonds we have. And over here we have a triple bond, which means we have 2 pi bonds. So those are the answers to those 3 practice questions, and hopefully this entire video helped you guys understand how to identify hybridization, sigma bonds, and pi bonds. And as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.